Well, hello everybody, and welcome to today's webinar. I'm going to get started in just a moment. Expecting another big crowd today, so I'll give people a minute to trickle in. In the meantime, I'm April Thompson, Senior Director for Bloom, which you're going to hear a little bit more about today from our presenter. This is set up as a webinar, so the chat function has been shut down, so we invite you to type your questions using the Q&A function, and we should have ample time to get to all of those. And with that, I am just going to go ahead and introduce our featured speaker today, Ron Alexander. Ron Alexander is a horticulturalist and president of R. Alexander Associates, and he has 40 years of experience in all aspects of compost, biosolids based, and other organic recycling product manufacturing, marketing, and utilization. We have worked with him at DC Water and Bloom for many, many years on field trials and market research, and have had this series for ASLA members and other interested parties for a couple of years now. And this topic actually came about when someone from a prior ASLA certified webinar suggested it. So we're excited to have you all here. Again, this is for a one ASLA CEU. If you are a member, you'll receive a link to a quiz at the conclusion of this, along with the recording of the presentation that you can review. And with that, I will turn it over to you, Ron.
Okay. Thanks, April. I appreciate it. It's wonderful to be here. Aside from working with organics and things like that, I have worked with using these types of materials in many stormwater and erosion control applications. Have written standards. And, this is going to be a step past, I think, introductory type data, I think, but I'm happy to be presenting it and being here today. And please note that people who are members of the ASLA have an opportunity to complete a 12-question test and get a CEU for attending. This is me. I will not go into it except to say that I have a pretty strong technical background. And I've worked on a bunch of stormwater projects especially on the West Coast, but also a bunch here in my state of North Carolina. Here are the topics for today. We're gonna talk about stormwater management, of course, but we're gonna focus on bioretention and infiltration soils, as these are really kind of interesting techniques, green infrastructure techniques that we can use that can blend in well into landscapes. So we'll get right down into it. Okay, so starting off here, why are we so concerned? What's the deal with stormwater? Well, we have a lot of issues going on. Number one, climate change. Weather patterns seem to be changing. We seem to have more unpredictable storms. We get storms, especially in the east, with greater intensity and energy. Also, in the region in which we're talking about, the DMV area, there's a lot of dense soils. So dense soils which don't perk well, they're ripe for more stormwater and erosion issues. When it comes to regulation and how stormwater management is managed, regulations are done at varying levels, but they're enforced, and even standards are made as low as on a local level. There are benefits to that. The negative aspects of that are making positive change. Modifying regulation is very painful and a slow process because it has to be approved down to a local level. Also, I've worked on many construction projects over the years. The construction industry is sadly sometimes pitted against stormwater because the more stormwater infrastructure you need on projects, the less structures you can build. Um, so this is an issue, and we're pitted against, sadly, the construction industry at times. Because of it, we also are very often have inadequate capacity for stormwaters. I mean, if people remember the major storms we had several years ago in New York City, where there were two 500-year storms within like 3 years, you would think that a lot of states would be ramping up their stormwater requirements to say if you build, you have to have capacity for 100-year storm. Um, but I was just doing a project here in North Carolina, and we're still regulating for 10-year storms, which is crazy to me. So, and on top of everything else, modification into amping up stormwater law is very, very slow because it costs money to customers ours. But the downside is when things go wrong, the damage for not having the infrastructure can be pretty, pretty bad. Um, at many, many levels of government, we understand that stormwater is a problem. Even you can go to the Department of Energy and Environment website, and you can see there's pretty detailed information up there on the concerns and how to deal with stormwater. And we'll get into it a little bit more, but there are major economic issues as well as environmental issues, as well as clean water issues when it comes to managing stormwater properly. If we whittled it down to three major areas to consider is water quality. Research has shown the more soil that moves, the more stormwater that doesn't get absorbed properly and runs along the surface of the soil, the more sediment goes along with it. It directly impacts the amount of pollution that gets carried, whether it's pesticides, nutrients, metals. Um, so protecting water quality and drinking water even is a major issue. Then we have protecting man-made structures, including landscapes. I would argue that improved stormwater on large landscape projects can be sold as insurance, because if we don't absorb water effectively on landscape projects, we have a lot more long-term damage on the landscape projects. And then, of course, we're also trying to manage stormwater to help manage and protect natural areas and wildlife. But there are human health issues related to it also. There's lots of ways to deal with stormwater. Obviously, gray infrastructure is primarily what we've had up until about 25 years ago. The West Coast, especially the Northwest, which the state of Washington, some places can get up to 100 inches of rain a year. Even though their intensity is low, they get a lot of volume. I've done a lot of work out in that part of the country, and we're trying more and more to use sustainable landscape practices, green infrastructure practices, to help manage stormwater. And of course, we've had great success using these technologies to manage volume, including peak flow, right? The highest amount of flow that happens during a rainstorm, which we attempt to manage, and minimizing localized flooding. And then, of course, we also try to manage the water that moves through those systems and decrease pollution. And the systems work quite well. We are still working hard at learning and getting better at maintaining the systems. This is something that's often forgotten in green systems, and we are getting better. But the concept of some of the sustainable management type systems is to imitate nature. Our goal here is to create some large stormwater management features that work like wetlands, for instance. Now, In the DMV area, we have issues with soils and topography, which makes stormwater more challenging. With more people, obviously, there's more buildings, so there's less green space, less area for the infiltration of stormwater. Um, there are even low-lying areas as we get closer to the water that are prone to flooding, and we have a bunch of very heavy clay soils that just don't um, perk very well. Now, going back a few years ago, I did a bunch of work with the Washington State Department of the Ecology, and they had major issues with damage to actually the Puget Sound, which is the bay, which has huge environmental relevance for both people who come and tour the region around Seattle, also the spawning and the growth of not only shellfish but also salmon, and they were looking for new methods to deal in erosion control and stormwater, and they got very, very heavily into creating infiltration soils. And I'll just mention briefly some of these graphics you see here. One of the things we had to do is educate the construction industry about, what really happens to all this water when we start building and we have more hard surfaces. Well, the easy answer, of course, is instead of moving vertically through decompacted soils, the water runs horizontally, and when it does, it picks up velocity and it takes contaminants with it to low-lying areas, often streams and things like that. So we have major erosion control project problems, loss of topsoil, and it causes a whole bunch of issues, including runoff, and the need for more irrigation. If water does not perk, we need more water to grow plants through irrigation. We have more problems with recharging water deeply aquifers under the ground, and we just have more pollutants moving. So here are some graphics that they've shown. Now, here, impact can be quite bad. I mean, we talk about things that happen on landscapes, but down here in North Carolina, we're actually, because we have heavy clay soils like in your region. I mean, people have heard about what happened in Asheville. We're getting mudslides. We have the Blue Ridge Parkway, where people come to watch foliage, that parts of the roads were covered and with mud or just basically collapsed. So the issues can be small to extremely, extremely relevant. But when it gets down to bringing it to construction projects and landscaping projects, if we don't deal with the stormwater, we have unhappy customers. And one of the things we had to do out west, legislation was going to be pushed through that said you will enhance stormwater management, which was going to cost more money. The allowance of using soils that infiltrate, the addition of materials to the soil to improve percolation, was approved as an allowable stormwater management technique. One of the things that I was involved in doing is actually educating builders who were going to have to deal with soils differently, but help them understand that they can sell the benefits of this to their customers. And there are people, landscape architects and landscapers and contractors, who are on this webinar right now. We need to consider for the marginal increase in cost to deal with some of these green infrastructure techniques for larger projects, and it is marginal. We need to be smart about selling the long-term benefits, the insurance that the homeowners get to reduce damage to their property. And this is just some of the tools that we used out promoting the healthy soil green infrastructure concept. Now, on the rest of the webinar today, we're going to talk about these landscape-based stormwater treatment options, green infrastructure. We're going to focus primarily on bioretention, which is extremely popular, and then something that really has a lot of potential moving forward, and that's creating infiltration soils on landscape projects. But if you see just the document off to the right here, just showing there's a lot of green infrastructure techniques. Each state and in many regions of certain states, they have allowable practices that you can gain credits for. And you have to make sure that in your region of the DMV, whichever state you're in a region, that you're meeting the localized regulation. So bioretention, that is really has become very popular over the past decade. And it's a wonderful stormwater treatment process consisting of basically soils that perk, having plant material growing in these manufactured soils to help facilitate infiltration, as well as capture, percolation, and also cleaning pollutants. Okay, typically these are the retention areas are in low-lying areas, obviously, so we're using gravity to help get the water gathered. The goal is to make them physically attractive. However, I will tell you that I've done a lot of work the past 5 years in California, and we have this constant battle with these bioretention features. We have to make the media that perks water, and we're constantly battling keeping enough water in the system to keep the plant material growing. And that's an ongoing struggle to these systems. And then, of course, based on how we're using the system, what the localized use is, there will typically be a number of inches per hour that the systems will perk. A typical starting point is 2 inches per hour, but it changes and it's different based on what you're doing and what your project does. So typical bioretention features are things like ponds and basins. Smaller versions are, of course, rain gardens. And then we have bioswales, which sometimes infiltrate water, and sometimes they infiltrate water and carry water to the larger system. I'll show you a couple pictures of them. But the weird part about this is that the terminology, if you go to different states and state regulations, these definitions and terms are swapped and makes it a little bit confusing. But we'll move along anyway on this. So here's a great graphic. This is something that's online. This picture is used in many educational presentations, but it's a typical bioretention feature. And it outlines the component. We'll just go through them quickly, and we'll get into a little bit more detail in a second. So, first of all, you have a bioretention media, which is a media that obviously it's got a lot of sand, coarse textured mineral material in it. But on top of that, we have a layer of mulch, which helps protect that layer from erosion and other things. It also can bind metals and such. The systems are built so water that comes in heavily can pond before it perks. Below the bioretention level is a gravel bed or another coarse sand bed, which also has the capacity to hold a lot of water before it perks into the existing soil. In many cases, or in certain cases, there can be inlet areas built through the system in between the layers where there can be perched water tables and clay that doesn't allow for the movement of water vertically. So we sometimes have to put an outflow drain in the system, typically in between that bioretention soil and gravel bed. And there also will be often some type of overflow spillway if too much water comes to capture the water and hopefully disperse it, not to cause damage. The other important aspect to always consider is there are these pre-treatment areas up on the top left. You'll see it's called an inlet from the roadway, but basically there can sometimes be concentrated flow that is entering into the feature. We want to slow that water down so it doesn't cause damage to the feature and cause erosion. So very often we have rock beds that will slow the percolation or the velocity of the water, and also allow certain soil particles to trickle down and fall out. So this is kind of, a simple design, or maybe not simple, but a detailed design here. And what you notice to the right here is the general depth of the different layers. Okay, so um, the design itself should, when done properly, significantly reduce runoff to a site. Um, Water is lost through or managed through the bioretention feature through evaporation, through transpiration, water that moves through plants, right? And then the infiltration. Um, Obviously, if we do it well, we're managing the volume of the water as well as water quality. Keep in mind, certain systems are built with deeper retention areas of media or water that moves through the media through design slower to improve capture of certain types of contaminants that are maybe relevant to that specific environmental area, right? So that would be designed not only based on the size of the feature, but the depth of the media and the capture area. Will also be related to the density of the soil below um, the feature. And here's a quick comments about that pre-treatment zone again. We very often use rocks and such to slow the velocity of water down. Um, and basically flocculate out some of that media or soil. Obviously, one of the things we want to have in the bioretention feature is vegetation. We more and more move to native plants, those that can use nutrients that get into the media and don't need a lot of fertility. Also, ones that have deep rooting to help keep the percolation of the media intact, and ones that can be visually appealing based on season of the year. The mulch layer, again, a key aspect here is to try to use a mulch that is what we call a non-floating mulch, which is a misnomer, a less floating mulch. We try not to use rocks as mulch in these systems. We want to use a mulchy material, stringy materials that hold together and that are a little heavier are often better as they don't float off of the or out of the feature. And that's a key aspect of it. So, some of these dyed mulches that are very high in carbon, you don't want to use them because they will readily float. Okay. The soil media we'll get to in a minute, but the goal here, of course, is for capture and percolation and cleansing, pollutant capture, right? Um, and provide a good, solid growing media for the plants. There's always a controversy pitting the type of the media, the organic content, the potential nutrients in the media, and the health of the plants. And it's a really problematic balancing act that we have to do as we're using these systems. Again, you can see off to the right there, you can see the media going on top of the storage bed, which in this case is a very fine gravel, also holds an awful lot of water. And again, the two other kind of infrastructural aspects to deal with excess water are potentially under drains and overflow structures, and we don't install them in every application. One of the key components to the system, of course, is the media. The media is primarily sand-based. It can be anywhere from really 60 to even 80 to 90% sand. Soil is often also specified in the mix. It's typically 2 to 3 main ingredients going into the media. We'll get into that in a second. And nutrient removal is provided primarily through the absorption to the media and microbial activity, as well as plant usage. But certain numbers of contaminants can potentially leave the systems. And so it's a balancing act to get the highest reduction levels of nutrients and pollutants and keep that system and the plant material growing and the system operating at high efficiency. Here's a localized spec from the DC DOT bioretention specifications. You'll notice that, well, again, what I mentioned a little bit earlier, the media is typically 60 to 80% sand or fine gravel. You want to minimize the amount of mineral fines in the mix, which could potentially clog up the movement of water or crust the soil surface. Down here in North Carolina, we've built a bunch of bioretention mixes, and we tried to get organics out of some of these mixes, and we put clay in instead, and the tops of the bioretention features basically seized up and crusted off, and the systems were not functional. So we're constantly learning how to improve these things. We don't have all the answers. We're getting better and better as time goes on with this. One of the struggles I've seen across the country is the specifying of the soil component. Typically, there's 2 to 3 media components in the media, and getting the sand or the soil, I should say, which is typically a sandy loam or a loamy sand. In some areas of the country, we just have a really hard time getting soil that meets the spec. So in those cases, we sometimes have to drop down to 2 major ingredients, the organic section of the mix, and then basically coarse sand. And again, I mentioned earlier, one of the key aspects here, we want to move water through the system to attempt to manage peak flow to the site, but also hold enough water in there that we can properly establish and grow the plants, right? We don't want any large chunks or stumps or noxious weeds to be in that media. And it is important to know that some of these specifications can be quite complicated and problematic to meet. Very often you see the 3 ingredients in that DC spec, the coarse sand, the base loam, and the organic material. Very often all 3 of those materials have their own specification, and then the final media has its own specification. Okay, so it can be quite trying to meet these specifications. And then on the bottom of that spec, you can see things like pH and CEC, cation exchange capacity, right? Salt content, which are relevant to helping the plant grow. This is a spec that was used a lot in the Bay Area. I did a bunch of projects with this specification. They don't always have soil in their specs, and they have quite high organic ingredient volumes out there. So that's just the way they're doing it out there. It is important to know that some of the specifications that are written can be quite complicated, and sometimes we have additions. I don't like using the term pixie dust, but we have little minor ingredients that are sometimes added. The new material that's starting to be added are things like biochar. I do not consider that pixie dust, but we're still learning how to use that. I actually think that that's going to be a great additive along with an organic fraction that could potentially degrade a little quicker, the biochar a little bit slower, but we're still learning about this. And the more complicated that we make the media without really good data backing up what we're doing in that design, the higher the cost, the harder it is to get companies that will actually bid on projects and build those mixes. So we have to be careful and smart as we're designing these mixes. Why do we add this organic matter component to the mix? We've talked about it a little bit already, but it primarily has to do to help introduce biologic life into the system. Without some carbon in that system, it's hard to keep the biology alive. Biology, microbes, I'm a horticulturist by training. They live on plant roots. They help plants absorb water and nutrients. We want a healthy biology in this mix, so we have to feed it. The organic matter also helps cation exchange, the ability to hold certain nutrients and metals and such, so it also helps benefit plant growth. And some of these materials provide slowly releasing nutrients. We'll talk about this more in a little bit. And some of them actually have certain metals like iron in them that are good, really, really good at the capture of other metals like zinc and cadmium. Okay, so there's a lot of benefits, a lot of reasons why we use these materials. Here are a couple standards from the DC DOT manual. Again, there's compost, which has been used for years now, off to the left, as you can see, and then there's an alternative material which Bloom Woody Blend actually meets and is currently being used for. So these are already being spec'd. The Bloom product is a rather unique material. It's produced by DC Water. It's made out of biosolids, which is processed through high pressure and high heat, which essentially pasteurizes it. And you can see this pile of the dewatered material right there. It's pretty high in organic matter. It's got a bunch of nutrients in it, but they're in very slow release form. We have pretty good data on that. It also has a decent amount of iron in it, which is good for pollutant removal. They produce a product which is 50% bloom and 50% bark, which is used as a compost alternative in many applications, including bioretention. That product is kind of being used almost exclusively out of the Bloom products when it comes to designing bioretention media. And this material has a large amount of bark in it, which has a high carbon content, so it helps the CN ratio to reduce the movement of things like nitrogen. The material also has phosphorus in it, but it has an exceedingly low percentage of water extractable phosphorus, under 1%. The Woody Blend, again, is being used or has been used in the past by some major construction companies in the region. Over the past several years, there have been thousands of bioretention features that have been developed with material. You can see a quote here near the end of this slide. We're not naming the contractor on their request, but they've been very, very pleased with the use of the material, the functionality of the feature, but also growing of the vegetation and keeping it alive. We have to remember we want deep growing plants growing in the features, and we want to keep those roots growing, and that keeps percolation rate up and infiltration rate up in these systems. Okay, very, very famous cemetery in DC. They're following one of the local standards of sand soil and organic matter in this mix. Um, this is a very interesting place to visit. There are a series of bioretention features throughout the cemetery. They've had great success in implementing this project. Obviously, they got some outside funding to make that happen. One of the reasons it's interesting to mention this one is because the Bloom Woody blend was actually used to top dress the turf. They had problems with keeping turf on this site, poor soil conditions. So they top dressed and they seeded into the Bloom Woody blend. Interestingly, Pope Francis has pushed the church on the sites that they manage to use less petroleum-based nutrients. So I don't want to say that, this process was Pope Francis approved, but I'm going to say that even though it's not really true. Okay, it's not really true, but I'm just going to say that these using products that are the nutrients released from the carbon-based materials that are very slowly released is a great benefit. Of course, the interesting thing about using Bloom on these sites is that it has slow release nitrogen. Under 5% is readily available, but it has a bunch of iron, which is also helps the chlorophyll molecule, so it keeps the grass pretty green, which is kind of cool. There are a lot of other examples of bioretention projects in the region, and the Chesapeake Stormwater Network it had a wonderful best of in 2023. The University of the District of Columbia built a bioretention. Basically, they created a planting area that would absorb a lot of water, captured underground in a cistern to deal with a parking lot that was kind of flooding the area. They've had great success with that. They used the Bloom Woody blend in the media. Payne Elementary did a similar type project. In this case, there was not a cistern underneath the ground, if I'm correct, but they basically were improving the soil. They were getting flooding of water because of the lack of percolation onto their sidewalks, and they built a kind of a more infiltratable soil to capture more stormwater. And again, they've had very, very good success managing the plant material there. This is a project, I think it's the last one I'm going to mention here before moving on, that I was involved with in North Carolina. The town that I used to live in and I live in again built this magnificent park, downtown park. It's a 3-level park. And we had such stormwater issues in this part of town that the park was built partially to build in excess infrastructure for stormwater. If anybody is interested, I wrote an article about this that's quite detailed. OJB designed this park. They're out of Boston and Philly, but this is a park outside of Raleigh, North Carolina. The cool part about this is the stormwater management components of this. All the planting areas have infiltratable soils that are high in sand, that contain organics. There are also, as you can see here, off to the right, you can see the bioswales here that the water leads into the systems, and the water perks down several levels, even goes off over a waterfall to reduce some of the sediment. So this is actually a wonderful example of creating a park, but fixing a problem for a part of a town that didn't have enough stormwater capability. And where we live in North Carolina, the soils are so dense that our problem with climate change is inland flooding and mud. So this is a very, very cool example. Note that this is a couple media designs used for green roofs, another green infrastructural technique to deal with stormwater. We're not talking about that today, but two major differences with these bioretention medias and the roof mixes typically don't use sand. They use a little bit of sand sometimes, but they use a lot of expanded shale or clay, which are actually mineral materials that are actually puffed up with under high temperature that can actually hold water. And they use organics in the mixes, but they usually use lower volumes. Typically, the thicker the mix on the roof, the more organics that are used. You've heard the terms intensive and extensive media, but that's not our discussion today. I know that nutrient movement for some is a concern. So I did a project for the state of Minnesota that had to do with dealing with the migration of nutrients and from bioretention and erosion areas. And there are some smart BMPs that we can use to help manage nutrients in these systems, like using native plants, making sure we have a good stand, establish the vegetation as soon as you can. Don't use more organics in the media than you really need. I would argue that one of the things we should be doing is looking at the slow release nitrogen content and the water extractable phosphorus content of the different ingredients in the mix. And it should be noted that even things like sand and other aspects or ingredients of these mixes, a lot of nutrients don't come off of them often, but metals do. So there are materials that leach, and we should be testing these materials and knowing what we're putting in the systems. And then you can see there are potentially iron-based additives that you could possibly add to some of these mixes. It is important to note that where the research has been done, and some of it has shown that we do have a little bit of nutrients or some nutrients that leach, they do reduce over time. And we have to weigh that concept of the organics and the nutrients in the organics with the fact that we have to keep the plants alive and the plants need nutrients. So we have to be, we kind of have to just be realistic about what we're doing when it comes to design of these mixes. We're not going to talk about this because time is getting short, but I did a lot of research on testing different organic-based materials, and we can test these materials for quick and slow release nitrogen and water extractable phosphorus. Look, this is compost research I did, and the phosphorus in compost is only about 2 to 20% available in the first year. Bloom products are a fraction of that. So we have to be realistic when we talk about nutrients, because we don't want to make a mix that's void of nutrients and then have people pump in chemical nutrients on top that are much more mobile in water. Okay. And finishing up here, I want to talk briefly about the creation and the use of infiltration soils. Some of the mixes are in the planting areas. Maryland has designs for these things that look very much like bioretention soils, but in many cases, we're just adding organics to dense soils. We don't add sand because sand is much heavier and much more expensive. And organics can actually create porosity in the soils while holding soil when it's dry out. Now, obviously, the denser the soil, the less they perk or infiltrate water. We want to be able to capture as much water as we can. It's not a simple thing to do. Remember, the more we build, the more hard surfaces, the more water is going to hit the hard surface or even soil that's compacted and move laterally. Our goal here is to try to create soils that are difficult to compact, and there may even be a requirement to decompact it over time. I will say, if we're serious about dealing with stormwater in cities, I think we have to consider putting thicker layers of finished soil down, not just 6 inches anymore, but to expand that up to a foot. And that could help us in stormwater capture that's being experimented with in other parts of the world and to great success. Remember, these infiltration soils, the goal here is to not have them crust on the surface, to accept water, to store water, to allow infiltration, to remediate the water as much as possible, and allow for recharge into aquifers while we're allowing vegetation to grow. Because if we don't have vegetation growing, we're going to have erosion, and that modified material that we just created is going to start pushing off the site, right? Remember, the coarser the material, the more pore spacing that we can create. If it's not a sandy soil, it's hopefully through microbial aggregation of the soils. The more water we can perk, the more water that sits in between particles and will move through gravitational flow after the site um, um, basically meets um, moisture capacity. Okay, remember this. Native soils are typically have more typically have better structure, which means they have more air pockets, which means they're lighter. As we compact soil and you look at a specific area, basically what that means is we're mushing the structure, we're losing air capacity, the soils hold less water, they hold less air, and you have more density because you have more soil particles in there. The key reason for me to bring that up is to say that it does not take much compaction to go from an ideal bulk density to one that starts affecting root growth to one which starts restricting root growth. As a horticulturist, I can tell you compaction to the soil makes plants use more energy to run their typical functions. So compaction is bad, and anything we can do to reduce that helps us not only with the plants, but also with creating long-term soils that will infiltrate water really well. I just want to show this really quickly. This is research that was done at Penn State. I use this. Sally Brown from the University of Washington and I did a manual for the ASLA to talk about how creating better, healthier soils are good for climate change. They're also good for stormwater management. The key thing you see, I don't expect you to study these slides, but they will be made available. When you add organic matter even into subsoils and sands, you lower the bulk density and you improve infiltration rate. That helps us on an ongoing basis manage stormwater. We've done research with Bloom Woody Blend. They work the same way. You add them to soils, you increase water holding capacity, you lower bulk density, and you increase hydraulic conductivity, the percolation rate of the soil, right? I want people to think about the fact that this is one of the things we need to do more of. When you build a bioretention feature, this is a project I worked on in Edmonton. Lots of times you can build a bioretention feature, and in the green areas that are used to slope water and bring water to that feature, if you actually make those soils infiltratable and have good vegetation on them, you can vastly expand the amount of water that the features can absorb, because the mild flows, a lot of that water is going to be absorbed on its way to the feature. This is something we need to do more and more. Washington State DOT, I did many projects with them. They had major problems with stormwater capacity on the roadsides, and also dissolved heavy metals, copper, lead, and zinc. And they started doing projects where you can see the stormwater inlet here, this 10-foot swath on each side of the road. They actually incorporated compost into that to create infiltratable soils. But the concept was to use the cation exchange capacity improvement to bind more of those metals. And if you can see here, here's our concentration reductions of the different metals. So it worked. Not a perfect system, but it's a living and an inexpensive system that can be quite functional. Also, by doing this, we also absorb more water and reduced peak flow. One of the big problems, whether it's a gray infrastructure or green infrastructure, is trying to manage peak flow where the highest volumes of water hit the management areas, okay? And we can't absorb it fast enough. So lots of times when we create these infiltration soils, it can reduce peak flow and the pressure on these systems, which can be overwhelmed at times. And there's been great research done showing the incorporation of organic matter, the creation of pore space through aggregation is a great benefit in the reduction of stormwater movement off these sites. BMPs are started to be produced that give us stormwater credits all over the country. Here's a couple more local in Delaware and Pennsylvania, and even in Maryland, where we're designing planting soils out of sand-based materials to help stormwater management, kind of like the project I worked on in North Carolina. We're seeing these happen more and more. So they're wonderful techniques, and a lot of these techniques can be used together and teamed up. Um, Final thoughts very, very quickly. These green methods can be very, very effective and creative in managing stormwater volumes. They can be very, very good at improving stormwater quality. We do have a major problem. Where climate is moving faster. Climate change is moving faster than regulatory change. So there's a lot of sites that do not have enough stormwater capacity, and it's something that we're going to have to concentrate on more and more. And there's a big, big room for catch up. And for that, I'll stop right there and just say that you can contact April and the Bloom team if you're interested in looking at these products to try to use on your projects. And I'm happy to answer any questions at this point. And thanks for listening.
Wonderful. Thank you so much, Ron. This is really interesting and inspiring. We do have a number of questions. So I will just kind of take these in the order they came in. Would a top dressing of a bloom type product increase the infiltration in an urban soil? Any research on that?
Yeah. Let me just see here. Let me stop my share. Let's do that. Um, there's not a lot of research in that area. So the greatest improvement to the dense soils when we top dress, whether it's with compost or with bloom, is first through core aerification. If we don't core aerify first, we're not going to get as much benefit for fixing the soil or improve percolation. The material sitting on the surface just doesn't, it's good, but it can dry out a little bit. And what we find out is through core aerification and bringing a little bit of soil into that mix, getting it into the soil a little bit, really improves its benefits in a lot of ways, including the acceptance of stormwater, because using core aerification, then top dressing, is a way to break up soil crusting.
Another question from Timothy. Specification that used 30 to 40% organic. Does the 5-inch per hour infiltration degrade over time?
Yeah. So basically, some of the mixes out there, or these are very, very specific mixes. Every mix that you put down within weeks, the perk rate changes. So basically, you're building these mixes knowing very quickly that the perk rates, once the material settles, still is appropriate for your application. So it does change over time. It's hard to say what the change is in years, because one of my gripes is somebody who likes to work on specifications, but wants to base that on good, sound research, is we haven't done great follow-up research in improving better maintenance techniques for bioretention features or monitoring the shift. That's starting to happen now over time, so we can remediate and fix the site. So it may be as simple as going in there with a deep timing unit that breaks up the media a little bit, and that may help us out. We know some of the media in certain places where there is a lot of heavy metal issues, we actually need to remove some of the media and replace it. And we're playing catch up in some of these maintenance techniques that I think hopefully we're going to do better at. So I can't give you a definite answer. I apologize, but
Thanks. Question from Christina. Any experience with sites with stormwater high in copper and how you would extract it out?
um, well, copper, um, certain organic if you're we used biosolids and biosolids copper. I'm from Pennsylvania to remediate um, mining sites in Pennsylvania that were very rich in copper and rich in zinc and also cadmium. So iron, I think iron is another metal that is good at binding copper. So there's a lot of good research out there if you look for if you Google that for the use of waste derived materials in those applications actually. Some of the metals are easier than other metals. The ones that bind with iron, iron is quite incredible how tightly it binds certain metals, and it works quite beautifully. So there's really good research on that. And if you send April or myself a note on that, we can probably dig up a couple things to send to you on that.
Yeah. Seneca, question. Can you comment briefly on the longevity of bioretention? What are the most common or most severe factors in degradation?
In degradation. A key aspect for any of these natural mixes or techniques is we need to have proper vegetative stand. People would ask me, well, we want to build carbon up in soils. Well, how do we do that? Because there are all these benefits to keeping the carbon intact. Well, if you're doing a bioretention media or you're doing a landscape bed, well, you're going to fix the soil first, and then you're going to mulch on an ongoing basis. And hopefully that mulch is going to break down and keep adding carbon to the system so you don't have shrinkage. You have worms taking it back down and replacing organics that continue to degrade. Keep in mind, the deeper you go into the soil, the less oxygen there is, the slower the organic matter degrades. So the organic matter does not disappear. Matter of fact, the organic matter is also moved, fine organic matter is moved in the films of water from the top surface. And we've seen this by incorporating materials in the top 6 inches where you can see the organic staining feet into the ground without any incorporation. So the organics do move, but they're slow. Okay. When it comes to turf, how do we keep organic matter in turf? We keep turf growing. If we screw up the turf and it goes bare, well, then the organic matter starts to break down more readily. So we can manage carbon in the soil, but we have to be diligent with how we manage the site. I hope I answered the question.
A question building on the prior question on copper, is there any research on the best soil type or plant type by contaminant type, or is it mostly a one-size-fits-all situation?
I am not an expert in phytoremediation, but there is a lot of research out there about specific plants that they use to pull specific metals out. So I believe,
And
depending,
mushrooms.
is that right?
Yeah.
And mushrooms, okay. So, so I believe based on what you're looking to reduce, you could probably Google that pretty quickly and find some data. I believe. Yeah.
This is a question I can answer. It was, have biosolids been used at UDC Firebird Farm in Beltsville? Believe at least one of the projects incorporates the Bloom product. I I don't believe we have. We have had discussions. In fact, we recently reconnected with their new green infrastructure manager, and I know their rooftop project is in dire need of replacing medium there and have started that conversation, but not as of yet. Um, Question again from Avery. How much is quote unquote parent material considered in sediment, not soil, type during creation? I.e., is there a standard? I'm referring to the notion that different sediments which have come from different sources can alter pH or change the chemical environment. Say, for example, if someone is trying to reduce the pH prior to infiltration, the use of medium coarse limestone gravel can be used. Um, and then there's a follow-up note. Are you monitoring the chemical interaction between bloom and the chemical features of the water pre and post filtration? Sorry, it's a mouthful, but hopefully you can see the question also in the Q&A if you need to
Yeah, we may
look at
have
that
to
again.
follow up after the fact in with this one, but I can tell you that perk tests have been done by the University of Washington with Bloom Media. The problem with some of the research is some of the research we do in the lab is through a cylinder and you make a mix, and it's really the worst case scenario. It's not exactly what's happening in the soil. And we also have to remember too that whenever we have movement of materials, but if the water is infiltrating or below the feature into like a clay soil, there's going to be further binding. This is a really difficult discussion because we have to be practical about it. We're trying to grow plants. There have to be things there. There has to be nutrients there. But I do think that the key is understanding the problematic pollutant where you're building the feature and help to design the media around that. And we've gotten better. We can do that at least to a degree now that we couldn't before. I will also say, as far as pH of water and things like that, there have been some really cool things done with these filter socks where they're using organically based materials in these filter socks to run the water through, and it filters through the sock, which modifies pH before it starts moving closer to the feature. So I think that there are clever things being done. We just have to kind of make sure that there's data to back them up, before we get locked into that it's magic, that it works.
Thanks. And last question, how frequently does bloom need to be applied and replaced? Is it like compost, which may be added yearly or less?
Yeah, I think it depends on the application. Um, you know, um, for a garden bed, if you put a decent amount of organic matter, stabilized organic matter in a like a planting bed, many cases, unless you're in the deep south and you're burning a lot of organic matter off, you probably really don't need to add it for a couple years, but it really depends on what you're trying to do. I did work with ball fields that could not incorporate organic matter into the soils because management wouldn't allow it. So they're doing core aerification and top dressing, which means they're top dressing once a year for 3 years to try to build up that organic matter layer in the soil. Then they're trying to better manage cover to keep it there. So it's going to be somewhat similar based on the type of bloom product you're buying. But remember, it's about managing the site after you get it in the soil. And there are things we can do or our clients can do to manage the site, which keeps the organic matter from turning into CO2.
Got one more question. It just came in from Kate. We're using 12-inch filter socks filled with compost to filter stormwater. How long will these function? And how much I think maybe that's area, can 12 inches manage?
I do not know. I do not know. However, if you send April a note, I will forward you to one of two people who developed the first the concept the has the patent for that, and they will have that answer for you. I'm happy
I
to do
know.
that too. Seriously,
Okay. Yeah, she's a fellow DC Master Naturalist, so I can put us in touch.
excellent.
And with that, thank you so much, Ron. Thank you everyone for joining. Again, it won't be simultaneous with the end of this since we have to upload the recording and all of that, but just look out soon for an email from Cooper that will have the link to the quiz, will have link to the recording, will include your information, Ron, if that's all right with you.
Yeah.
And yeah, be in touch with any questions. Thanks again.
Thank you. Have a great day. Stay warm.
Thanks.